Come on. All right. So I'm gonna open up this, and now this presentation, it is on. Can y'all see that?
Yes.
Okay. So this presentation is actually on. It'll be on Blackboard. I can't remember if it's already up there or not, but you'll have it. So don't worry about like scrambling trying to copy all the structures down and stuff like that, because you'll have access to this. All right, but let's go to, so we're going to talk about organometallic coupling reactions. And a lot of times when we talk about coupling reactions, the main application for organometallic coupling reaction is to form new carbon-carbon bonds. Like these are, and we kind of talked about this already with the hydroxygenation and the borane chemistry on triple bonds, but we're going to kind of extend that. And then we got a couple of other topics that we're going to discuss after this. But so one of the critical species to be able to generate is this, what we call a vinyl lithium, which is this species right here, right? This is a vinyl lithium, right? And we call it a vinyl lithium because of what it is. You can look and see that there is a alkene, which is your vinyl group, and then the lithium, which is covalently bound to it, right? So that synthesis of that vinyl lithium, again, is a great precursor to other organometallic species, right? You can take that vinyl lithium and basically do anything with it. If you're wanting to extend a carbon-carbon bond framework or something like that. But the way you make vinyl lithiums is through this process here called the Bamford-Stevens-Shapiro reaction, where you start with a ketone, you treat it with this azide, and then 2 equivalents of butyllithium, and you're able to generate the vinyl lithium. So the key to this reaction is the loss of nitrogen gas, right? And that's shown in that this step right here. Hold up, I need ink. So in this step right here, right, that's the key to the reaction, because the first step is simply the formation of an amine. And then when you add butyllithium, you're going to deprotonate here. And that's where you have a negative charge here, right? So with that, that's going to facilitate the loss of nitrogen gas later on in the process. But here you lose the tosyl group, right? And now you're here. And then you add that second equivalent of butyllithium in order to deprotonate nitrogen, and then you lose nitrogen gas, which is the driving force for the reaction. And then your second lithium comes in, and now that's going to be covalently bonded to the that sp2 carbon in the double bond, right? So again, vinyl lithium is very, very versatile for coupling reactions with all types of different substrates, right? And we've already talked about hydroxygenation, which we talked about, I think it was maybe last week or week before, all right? And this is mostly done on triple bonds, because if we do it on double bonds, again, you get that chain walking and beta hydride elimination, which you don't want. It diminishes your yield for one thing, and then number two, you can't control it, right? So it's really not the process is not amenable, or double bonds are not amenable to this process. So triple bonds work better, right? So here you're going to get a mixture of products if you have a disubstituted triple bond like the one we have shown. So you're going to get the zirconium at either side, right? But the way you can also take the vinyl zirconium species here and convert it to the other species by adding in another half equivalent of the CP2 zirconium hydrochloride. If you do that, you're going to get this species, which then beta hydride eliminates to give you the more stable isomer, right? So that's how you're able to convert the isomer, the unwanted isomer into the more stable isomer. And so with again, the vinyl zirconocene complex, which is here, you can convert that to all types of different stuff. You can convert it, if you add bromine and MBS, you can convert it to a vinyl bromide. If you add iodine, you can convert it to a vinyl iodide. If you add a carbon monoxide, you can convert it into a carbonyl, which then the zirconium can be, you can kick that off by adding in a nucleophile and either esterifying that or converting it to an acid, so on and so forth, right? But again, all of these precursors right here, well, I'll go here. The vinyl bromine and vinyl iodide are very important precursors, right? Because those are precursors for other coupling reactions, right? They're precursors for like Suzuki coupling or not Sonic-Ashira coupling, but Suzuki coupling, Stille coupling, Heck coupling, so on and so forth, which we're going to talk about. Right, so hydrozirconation is another way to synthesize precursors for coupling reactions, just like making a vinyl lithium. And let's look at now some application. And so this prostaglandin synthesis is one application from the 80s where these coupling reactions really started to become popular and heavily utilized, right? So if you look at this prostaglandin, alprostadil is a derivative of prostaglandin. Prostaglandin is like a erectile dysfunction suppository, right? It's a urethral suppository to help treat erectile dysfunction, right? But you have 3 stereo centers that you have to set, which is here, here, and here. And then you also have a alkene here that you're attaching to that 5-member cyclopentanone, right? And then you also notice, we've talked about these already, these are protecting groups like the benzoyloxy group, as well as the TBS group. All of that is there to protect those alcohols, keep them from reacting with other functional groups, while you're doing your synthesis. Right, so the prostaglandin is here, and then if you look at the synthesis of one fragment, part of the fragment, right? You got you do a conjugate addition of this. Sorry about that. You do a conjugate addition of this zirconocene right here, right? And where do you think we built that from? That zirconocene. How would we go about get into this species right here? What would you do? Right, when you see a vinyl zirconium, what's the precursor to that? What do you think?
Alkyne.
It's an alkyne, a triple bond, right? So you this particular compound right here more than likely came from an alkyne. Let me pull up a blank page here. So more than likely came from something like this, right? Where the TBS group is already in there, or you could start with the alcohol and then treat that with TBS chloride to give you this, obviously because you don't want it to react with zirconium, right? And then here now you can just treat this with CP2ZrHCl, right? And get that vinyl zirconocene that you need, right? The one that you need for that reaction, right? And so when you look at that, again, that's the application of that technology, because those vinyl zirconocenes, you have to start with an alkyne, right? You cannot start with an alkene because, again, once you add the zirconium across the alkene is going to walk the chain and continue to do beta hydride elimination down that chain, right? So when we look here, again, we start with the vinyl zirconocene and we add that into here through conjugate addition, right? And let me give you a little bit about what that is, the conjugate addition, because that's another important reaction, right? Conjugate addition, or what we call, it has a name, we call it Michael addition. If you have a alpha beta unsaturated carbonyl compound, like so, we call it alpha beta because this is the alpha site and that's the beta site. So alpha beta unsaturated. When we have an alpha beta unsaturated compound, we can add a nucleophile to it, right? And that nucleophile, now keep in mind, this compound you can do, my bad, let me fix that. You can do 1,4, which is what we call conjugate addition, 1,4 addition, or you can do 1,2 addition, right? Because if you start counting here, this is 1, 2, that's 3, and that's 4. So 1,4 addition, the nucleophile would attack here. Right, so that's what we would call conjugate addition or Michael addition. And then 1,2 addition, it'll attack here, right? So if your nucleophile attacks at the 4 position, you'll get this compound. All right, if it attacks at the 2 position, then you'll get this compound. I'm just gonna put it as OH because normally you'll have to work it up, right? So the 1,4 addition is usually favored. It just depends on what the nucleophile is, right? The 1,4 is going to be favored with soft nucleophiles. Right, and that gets into, I'll talk about that in a second. So, and then the 1,2 addition is going to be favored with harder nucleophiles. I want to say harder. Right, so hard and soft nucleophiles are that's kind of a concept, comes from a concept of what we call hard, soft, acid, base theory. Right, and what that says is that it basically gives criteria for the types of nucleophiles and their preference for reactivity. So a hard nucleophile sorry about that. Hard nucleophile is going to be small, densely charged. All right, so it's going to have a dense, really, how do I put this? The charge is going to be so it's going to be highly charged, dense, kind of close to the nucleus. That's what I mean by densely charged. So it's like a really tight molecule. If I had to compare it, it would be like a marble, right? Whereas a soft nucleophile will be more like a dandelion. Right, that's going to be a big atom, so a larger atomic radius. And the charge is going to be more diffuse. Right, so a diffuse charge. If you were comparing atoms, it would be like comparing a fluorine with a negative charge. Right, so that'll be a little kind of a small, densely charged atom versus a sulfur, right, with a negative charge. Right, much bigger, charge is more spread out. The charges, the surface area is larger, so the charge is more spread out. So with 1,4 addition, the 1,4 attack is going to favor soft nucleophiles, and then the 1,2 attack is going to favor hard nucleophiles, because that carbonyl carbon right here will be it's hard because it's sp2, so the electrons are a little closer to the nucleus, and it's just it's a tight, more tightly bound electrons, because you know the electronegativity of a atom changes with its hybridization state, right? If it's sp2, it's going to be more electronegative than something that's sp3, right? So that's going to be considered a hard site, and this will be considered a soft site, right? So that's the basics of conjugate addition. And one other thing about conjugate addition is that when you add to the 4 position, right, you add a nucleophile to that position here, you can actually trap. You can trap that adder as a siloenol ether. So let me put this. It's got to be the right order of addition. So you add your nucleophile first. And then something like TMS chloride. Right, and then over here you'll have a trapped enolate, right, where your nucleophile is added in. So that's kind of a bonus, right? Because you can also think about this as a precursor to the aldol addition or some other type of addition. So the 1,4 addition adducts can be trapped as siloenol ethers. All right, so let me go back to here. So you can see here, where you did again, you did the 1,4 addition at this alkene, and then you end up with this product. So again, that's a you could consider that, even though it's a sp2 hybridized carbon, you could kind of consider that being a softer nucleophile in this case. And it's a nickel catalyzed reaction also, right? You can see that right here with nickel ACAC as the catalyst. All right, so once you get that, you can see the trapped enol. In this case, it's a zirconium enol that you add formaldehyde to, right? And that is going to give you an aldol product, which is right here, right? And the stereochemistry is controlled by this group right here, right? In the initial step, the benzoyloxy is controlling the Michael addition, right? So you add here and you can see that the stereochemistry is opposite on each side. And then when you do the aldol part, this is going to control the incoming aldehyde, right? And so that's why you see this bond here opposite to the bond that's adjacent to it, right? So all of that is based on this pre-existing stereo center here, right? It kind of controls all the stereochemistry. So there's no need to do any asymmetric catalysis or anything like that to set those stereo centers, which is awesome, right? Because again, if you can set it by using the pre-existing stereo center and get the selectivity you need, that's great. Right, so with that fragment in hand, now you have the hydroxyl group here, which you just converted into a mesylate and then treated with a base to eliminate, just a simple E2 elimination. And now this is ready to do another conjugate addition, right? You got your zirconocene here, which you can get from the alkyne precursor of this compound, same catalyst, nickel acac, to do the 1,4 addition, and then you end up with this zirconium enol right here, right? And then from that point, all you do is treat it with a proton source, and you actually built up this whole fragment, you know, in less than 10 steps, which is awesome, right? When you're doing a total synthesis, one of the keys to doing it is to do it in as few steps as possible. And the less steps, the more efficient that synthesis is, the more scalable it is. You think about if you're making a natural product or a natural product analog like this prostaglandin molecule, if you only have 5 steps and you're trying to get this, kind of translate this from the benchtop to actual, you know, practical use, the less steps, the better. All right. So this synthesis was achieved using these 2 conjugate addition reactions. And then again, the conjugate addition dominates over the 1,2 because those vinyl zirconocenes are considered soft nucleophiles, right? And I imagine it's soft because of the carbon zirconium bond. And the way that's polarized is probably diffuses the charge quite a bit with the metal being covalently bound to carbon. All right. Any questions about that part?
No, sir.
All right. So that's, again, you can see the application immediately. Many times these coupling type reactions or these organometallic reactions, they're always going to be tied to some type of synthetic protocol. Like you don't develop the method just to develop it. You always develop it with a target in mind, like a synthetic target in mind. So right, so let's look at cuprates, because this is a second synthesis of prostaglandin, but it's just using a different methodology. So in this case, they used copper as the metal rather than zirconium, and they built this up using this cuprate chemistry. So if you remember from Organic 2, if you took my class, we talked a lot about cuprates and these organocopper compounds, right? So if you take copper and react it with an alkyl lithium, then you can actually build a what's called a Gilman reagent or a cuprate from an organolithium plus copper. All right. And so normally the way you build up a cuprate is, you see how there are 2 groups attached here, right? Normally you take 2 equivalents of a vinyl lithium and you react it with like copper iodide or something like that, right? So to build that up, you add both or add two alkyl lithiums or organolithiums to copper. So you're going to end up with this cuprate with these two groups on it. The problem with the cuprate is it only transfers one group, and after that it's useless, right? You can't do it, you can't use it more than once. Once the reaction happens and that group gets transferred, it's done. So if you put two really complex substituents on copper, you're going to end up throwing away the other piece, and it's useless. So a lot of times what you'll see is people put what's called a dummy ligand on copper, and that alleviates the wasting one of those ligands. Normally your dummy ligand will be like an alkyne, because the alkyne is like, it binds really tightly to copper due to back bonding. I think we talked about back bonding. I don't know which lecture, but I know we talked about it, where the d orbitals on copper overlap with the p orbitals on the alkyne, and so when that happens, that's a really tight, a really good overlap, good interaction. So that alkyne binds really tightly to copper, and that we call that a dummy ligand, right? It'll never get transferred because it's too tightly bound to copper to get transferred. So this is a way to avoid like trashing one of your ligands that you synthesize. Because if you look up here, one of these groups is just going to get trashed, because when you do the Michael addition with the cuprate, only one of those groups is going to get transferred to that molecule. And you can see that here. And again, it's the same thing where the stereochemistry is controlled by that benzoyl oxy group out here. All right, so you got the benzoyl oxy group here, and it's going to control that stereochemistry because of its orientation, right? So that group is going to come in opposite to it or anti to it. And then again, now you can see you have your like a lithium enolate, which can then be used as a nucleophile to react with another species, which in this case, they're taking this iodide and reacting it with that to add in that top piece, right? And I think there's a typo, because it should be there should be a vinyl iodide, if I'm not mistaken. Well, it should be a vinyl group here between these two carbons. I apologize for that. So that's their method of building that up, and you can see right away they did that in 2 steps: cuprate addition, and then followed by enolate addition. Right. So 2 steps: maintain stereochemistry. You got all the 3 of your stereo centers set. But they did it instead of using the vinyl zirconium technology. They used the cuprate technology. So for cuprates, again, these are very valuable, right? And it's not necessarily a catalyzed reaction. The cuprate itself really acts as a nucleophile. So in a cuprate, the copper has a negative charge on it, and then the lithium is just a counter ion to that copper, right? So you can see here, right, they just started with, if you look at how they built this up, right, they just started out again with a 1,2 addition of a vinyl nucleophile, and the hydroxyl group, once you protect it with a large silane like TBS, that's going to direct your nucleophile to attack the 1,4 position anti to it. And then the same thing here, when they add in the iodide, right, that when that attacks, that's going to also come in anti to the substituent that is adjacent to it, like that, right? But again, this is a different type of technology, but same outcome, which is to get to that prostaglandin. So here's how cuprates are built up. You can use copper bromide, copper iodide. If you add one equivalent, the copper organometallic species and that can be alkyl, aryl, or vinyl, that R group, it doesn't matter. And then so that's added, and then you add another equivalent of your organolithium, and then this is soluble, right? This cuprate is soluble. All right, so you have two groups attached to it, but only one gets transferred. And then so your rate of transfer is shown down here, right? So sp2, alkyls, vinyls already, that's going to transfer the fastest. So aromatic and then vinyl groups transfer faster than sp3 groups, and then the sp transfers the slowest. So that's why your dummy ligand most of the time is going to be an alkyne, because the sp hybridized carbons, when you attach that to copper, it's going to backbond with the d orbitals around copper, right? And so that's a really strong interaction, and when that happens, it slows down the rate of transfer tremendously. All right, so we've already kind of talked about this, where you can take the cuprate, which is also a soft nucleophile, and here you have dimethyl copper lithium. You could treat that alpha beta unsaturated ketone with that, and you're going to favor that 1,4 addition, where one of those methyl groups gets transferred to the beta carbon, which is here. And then, so this intermediate enolate, you can treat with TMS chloride and trap it, or you can treat it with a nucleophile. And you can see right here, with an electrophile. So benzoyl bromide, you treat it with benzoyl bromide, and you can add this piece on here, right? And this is kind of oversimplified because that 1,4 addition, without any bias in the transition state or any pre-existing stereo centers, you're actually going to get both isomers. So this would be wedged or dashed. All right. And so those cuprates are easy to make, and they're also relatively stable, easy to work with. And again, it's not a catalytic process. The copper itself actually acts as a nucleophile. So it actually attacks, because it has a pair of electrons on it. It can attack an electrophile and then transfer a group from itself to that electrophile in like a coupling reaction. All right. So we're going to talk about a bunch of different coupling reactions with the mechanisms, but I don't want to do that before I do the FK506 synthesis, which we're going to talk about on Monday, because Friday we're going to do finally, unless we got another holiday or something, we're going to do those papers that I sent to you. So I want to stop here, and then we're going to pick up on Friday discussing those papers, and then Monday we're going to talk about, again, all of this zirconocene technology, cuprates, all that stuff is going to be included in that FK506 synthesis. And I'll send you that paper so you can be looking over it. And then we'll do a presentation on that on Monday. And then Wednesday, we're going to get into these coupling reactions. We're going to talk about the Steely coupling, the Suzuki coupling, Sonic-Ashira coupling, and head couplings. And I'll make sure you have this PowerPoint. All right, any questions about anything?
Okay, no problem.
All right, and I'll post this recording to Blackboard. Not Blackboard, to YouTube as soon as it's done processing.
All right.